Dear friends, we know that the liquid particles in contact with each other as well as the solid liquid particles in contact with each other opposes the relative motion of each other. The opposition to the relative motion of liquid particles or solid particles in contact with liquid is called as the viscosity. The force with which there is opposition to the relative motion between the liquid particles or the liquid layers is called as the viscous force. Let us consider there is a spherical body which is moving in a liquid. As the spherical body enters in a liquid, it displaces the liquid particles, and liquid particles which are close to this solid sphere will come close to each other with the liquid particles, and the contact of solid and liquid particle and contact of liquid and liquid particle opposes the relative motion of the spherical body. Stokes has given the Stokes law for the viscous force acting on a spherical body moving in a liquid having coefficient of viscosity eta. According to Stokes' law, the viscous force for a spherical body of radius r moving in a liquid of coefficient of viscosity eta with a velocity v is directly proportional to the coefficient of viscosity, is directly proportional to the radius, and is directly proportional to the velocity. Therefore, this viscous force acting on a spherical body moving in a liquid is given by 6 pi eta r into v, where 6 pi is a constant of proportionality which is found by the experiment. This Stokes law is verified dimensionally. The dimensions on the left hand side of the equation and dimensions of the right hand side of the equations, if they are same, we say that this equation is homogeneous and dimensionally homogeneous, and it is the correct equation. The dimensions for this viscous force are m1, L1 and t minus 2. 6 pi is a constant, it is dimensionless. Dimensions of the coefficient of viscosity r. This is m1, L minus 1, t minus 1. Dimension for r is L1 and dimension of velocity r, L1 and t minus 1. Therefore, you will see that it is m1, L1, t minus 2 is equal to m1, L minus 1, L plus 1 get cancelled. Therefore, it is m1, L1 and t minus 2. As the dimensions on either side of the equation is the same, the equation that we have written for viscous force for a falling sphere inside the liquid is correct formula given by Stokes. This is the Stokes law and the Stokes formula for determining the viscous force on a spherical body moving in a liquid. Hereafter, we are going to explain a very simple formula for coefficient of viscosity and the method to determine coefficient of viscosity. For that, we will do a simple thing. Let us consider there is a cylindrical tube. This is a cylindrical tube of sufficient length. One end of the tube is closed. Let this tube is filled with a liquid whose coefficient of viscosity is to be determined. This is the liquid inside the cylindrical tube of which coefficient of viscosity is to be determined. Let us consider there is a spherical body of radius r. Let us consider there is a spherical body of radius r. Let this spherical body is nothing but it is a spherical bob of metal whose density is rho. Rho is density of spherical bob, or it is the density of metal of sphere. Let the spherical bob is moving in a liquid whose density is sigma. Sigma is density of liquid in which the metal sphere is moving. Then various forces acting on the spherical bob are: number one, the gravitational force acting on the sphere, which is called as the weight of the sphere. It acts vertically downward. This gravitational force acts vertically downward. This is the gravitational force which acts vertically downward, which is also called as weight. And what this weight is equal to? mg. The second force acting on the sphere is the viscous force, and this viscous force acting on a sphere moving in a liquid is given by 6 pi eta r into V. This viscous force depends on the value of V. Here we will think of a little bit physics here. What is that? When the spherical bob is moving down, it is acted by a gravitational force. Therefore, it has acceleration due to gravity. Because of that acceleration, there will be an increase in velocity of the moving ball. With increase in velocity, there is increase in viscous force. The direction of viscous force is vertically up. It is not constant, but it changes with the velocity and it goes on increasing as it comes down. This viscous force acts vertically upward. This is the viscous force acting vertically upward. As it comes down, the viscous force goes on increasing. One more force that acts on a spherical body which is moving in a liquid is the upthrust. And the upthrust, or we call it as the buoyant force. The buoyant force acting on the spherical body is the volume of the spherical body 4 by 3 pi r cube into density of liquid. It is sigma into acceleration due to gravity. How this force is? This force is vertically upward. These are the three forces acting on a spherical body. One is a downward force, other two are upward force. This force increases with velocity. Velocity increases with distance inside the liquid. After traveling some distance, the stage will reach in such a way that the viscous force is equal to viscous force is raised to a value in such a way that the sum of the upward forces, that is viscous force plus the upthrust, sum of these two forces will become the force due to gravitation. Initially, what will happen? The gravitational force is more than the sum of these two forces, and because of that the net force is acting downward, and hence the spherical body is accelerated. There is increase in velocity. With increase in velocity, there is increase in viscous force. With increase in viscous force, sum of these two forces, when it becomes equal to the gravitational force, thereafter a equilibrium is reached. There will not be a net downward force acting on the bob. When upward force, viscous force plus the upthrust, when these two are equal to the weight, the net force acting on the bob is equal to 0. Net force is 0, net acceleration is 0, and thereafter there will not be any increase in velocity, and 0 acceleration means 0 change of velocity. 0 change of velocity means constant velocity, and this constant velocity is nothing but the terminal velocity of the spherical body. Now, in this condition, the weight is m into g, but actually what m is 4 by 3, the volume into density into acceleration due to gravity. Volume into density is the mass, m, into acceleration due to gravity. The viscous force is 6 pi eta r into v. 6 pi eta r into v plus upthrust, I will write, it is 4 by 3 pi r cube sigma into g. 4 by 3 pi r cube sigma into g. This is the relation that we get. Now, with these two, what I will get? With these two, I will write here, it is 4 by 3 pi r cube in the bracket rho minus sigma into g is equal to 6 pi eta r into v. By bringing this upthrust force to the left hand side, I will get 4 by 3 pi r cube rho minus sigma into g is equal to 6 pi eta into r into v, and from this I will write an equation for coefficient of viscosity. Now this pi get cancel, this 4 get cancel with 6, 2 2s are 4, 2 3s are 6. This r cube will become r square by cancelling 1 r. Therefore, coefficient of viscosity is 2 divided by 9. Coefficient of viscosity is 2 divided by 9 r square in the bracket rho minus sigma into g divided by v. This is the required formula to determine the coefficient of viscosity of a liquid, and if the coefficient of viscosity is known to us, we are able to determine the radius of the spherical bob, and if the radius of the spherical bob is known to us, we are able to determine the coefficient of viscosity. This is all about Stokes' law, terminal velocity, and how to determine the coefficient of viscosity using a simple experiment. Thank you very much.